So now we're going to start to see how we can use regression to tie in with the word problems we've been doing. So the first question says, a scientist in a laboratory collected data about the number of bacteria in a sample. The results are recorded in the table below. Now, for all of these problems, if you are actually doing this, either you have knowledge of the situation that tells you should use a type of regression, in this case we're using exponential, or there's a lot of statistical measures to decide which type of regression is best. We looked at scatter plots the other day. That's one thing you can do, and there are more, algebraic type methods that people use, computer technology, things like that. For now, and in this course, they're just going to tell you use exponential. So for this problem, I'm not going to use the calculator. If you need to see how to use the calculator, you can go back to the previous lesson, lesson 60. I'm just going to write down the equations that I got from the calculator. So for this one, for exponential, rounded to the nearest hundredth, when I enter in this data, I get 20.51 times 1.92 to the x. Now, this is sometimes a tricky question, the next part. We're not starting to make predictions. We're just saying, okay, what does that equation tell me? So the first thing we know from an exponential equation is that the first number, the a value, is the start number. So that means at the beginning of the experiment, or when the observation began, there were 20.51 bacteria. Now, we can see in actuality that there were measured to be 20 bacteria. But if we're looking at the parameters of the regression equation, which considers all the points, that is the number that's predicted. So even if we maybe didn't have the data point of 0 to 20, we could predict how many we started with. Notice context of the problem. That means I can't just start with 20.51. I have to write this in what the problem is about. So the second parameter, which is the b-value, which is 1.92, tells us something else. That tells us each time period, so in this case, each hour, the bacteria increased by 92%. And we know that because we can take the 1.92, subtract 1, which is 100%, and we get 0.92, and we can tell that's an increase of 92%. So each hour, the amount of bacteria increased 92%. So we're close to doubling, but not quite. So now that we have that done, we are going to go through, it says, and do some predictions. So it says, using a regression, how many bacteria will be in the sample 4.5 hours after the observation began? So we can use our equation. We have to decide, is the 4.5 hours, would that go in our x column or our y column? And it would go in our x column because that's our hours. So we have an x value of 4.51, and I think it's good to make this statement. It's quick, and then we can see which variable we're plugging in for. I always check for rounding, so I want nearest whole number. And if I take this in my calculator, I am going to get 386 bacteria. So the next one says, algebraically determine to the nearest tenth of an hour when there will be 2,000 bacteria in the sample. And we're going to verify with a graph. So algebraically, first off, this is a y value, because y, if I look in my table, is the number of bacteria, and that's what they gave me. So I set my y value equal to my equation. And I'll use my solving techniques. I know I need to get rid of the 20.51 first. And that's going to give me approximately 97.51 equals 1.92 to the x. I have Ben form, so now I need to put in Benny. And when I take that in, we want to the nearest tenth of an hour. It actually rounds to 7.0 hours if If you did not get exactly that, or you got something that rounded to something slightly different, it meant that you rounded at some point too early in the problem. So that's our algebraic method. We're also going to try the graphical method, just to show that this is another option that you can use. So in order to solve this graphically, we know any equation can be solved graphically by graphing both sides of it. So I have, if you watched my last video, I have a lot of other stuff going on. If you see a plot going on and you're doing nothing with a stat menu, get rid of it. So I'm graphing 2000, I'm graphing 20.51, and since they told me to round in a previous problem, that is what I use. I don't use that whole regression. If they told me to round in part A, then I'm using that for the rest of the problem. Now, thinking about my window, I know my answer is 7. 7 is the next value. So my window, I'm probably just going to go 0 to 10. 0 to 12 would have been fine too. For my y values, I need to go all the way up to 2000. So maybe I go from 0 to 2100. I want to make sure that I see the values that I need. So now I see my graph, and I'm just going to draw a little sketch of this. That was not in the right place. So if I label these, this is my y1 and my y2. And it doesn't really matter which one, but then when I write that, I try to do color coding. This is my y2, this is my y1. This point of intersection is second calc intersect. We could move over to it, but there's only one point of intersection, so it's going to find it either way, is 7.0, if I round to the nearest 10, 2000. So I see the same answer from my graph as I would from the algebraic method.